Our next talk is something that is very dear to me. One of the things that I felt is that moving from single system to distributed systems, when it comes to debugging, we went retro. The powerful tool that was actually available to us was printf. And it was up to the engineers to collect all the logs or actually have something that actually broadcasts these grep statements. So Sundaram is coming up here to talk about LogLens, which is a system that he and other engineers built in Twitter to make this substantially easier. Please welcome Sundaram.
So good morning, everyone. My name is Sundaram. I've been at Twitter for about closing on 2 years now. And I'm here to talk about the first thing I worked on at Twitter, which is find a solution to manage service logs in our data center. Overall, I'm going to talk about sort of why on earth would we want to address this problem, a little bit about the characteristics of the problem, and how our Hack Week solution didn't really meet our requirements when we got adoption, and then finally a little bit about our current architecture. Okay? What is this? Oh. Yeah. So before I dive into motivation, one of the things I want to talk about is how Stateless Services use our compute tier. And if I am an author of a stateless service at Twitter, and there's a lot of stateless services, the interface I see from our compute tier is that of a job scheduler to which you submit a job definition. And the job definition consists of multiple things. One of them is how many instances of your job you need started up, the package and what kind of processes that you need as part of your job, and your resource ask, right? How many cores, how much RAM, and how much disk. So when you submit a job definition like that to the scheduler, it's going to start up n sandboxes, and within each sandbox, it starts up your processes and applies resource constraints to that sandbox. You can get rescheduling events, and when you get a rescheduling event, the particular instance is torn down, and it's restarted on another machine, and you get absolutely no state translated over. It starts afresh. And that's perfectly fine for stateless services. And the only real good state that stays on the box that you lose is service logs. So at least for us, we need a way to externalize service logs and guarantee retention periods about them, because not having retention periods for your service log means triage is really, really hard, right? Sometimes you say you can do it, sometimes you can't do it, and that's not a good state to be in. A second property of building services like that is that the typical service is n identical instances to which you talk through an RP by delivering RPCs to it. A client of such a service has a client library which does automatic service discovery, finds out what are the active instances at this point, delivers RPCs to them, and it has its own heuristics to decide where to deliver RPCs. So if you're looking to trace requests, you are stuck with the challenge of searching across all the logs and probably dead instances and live instances of your jobs. Okay? So it definitely helps a lot to have a single place to go to which offers performance search and a good user interface to go search across logs for all your instances. And the last thing that's interesting in this space is consistent experience. If you're a developer, you're working on service A, you go to service B, and you want to troubleshoot similar problems, you don't want to relearn this stuff again. It should be like build. It should work exactly the same when you move from one service to another. And similarly, if you're the owner of service A and you talk to service B, things get lost between services, and you frequently need to triage between them. And so you should feel empowered to go look on the other side, right? And so this helps if you have a uniform framework for this. So hopefully that's enough reasons to go actually address this problem. So if you've decided to go address this problem, there's basically 3 areas in which you can make your investments. Frequently, most people make it in all 3, but they're aggregation, search, and analytics. Okay? In terms of aggregation, the kind of investments we made were primarily asking clients to integrate our libraries and having our libraries push out data to our backend. That's the way we aggregate. And the choice to do it that way was mostly because we want to operate with a small team, and dealing with too many formats is annoying, right? And also, we have a central place to add value, like trace IDs, additional things that help specific troubleshooting scenarios, etc. But we don't actually deal with syslogs and stuff like that. This is primarily targeted service logs at this point. Search is our bread and butter. We have made a fair amount of investments there. And we have made almost no investments in analytics, which might seem surprising. Most of the investments are basically aggregations on top of search, which aid visualization. And the reason we have no investments in analytics is because, and if you compare it to some of the commercial products which tout deep log analytics as being essential to your data center or your system, the reason we don't do that is most of the value that comes from those scenarios comes from sort of 3 separate products, one of which I'm talking about. The other 2 are your metrics infrastructure and alerting, right, which are tier 0 services. You're flying blind in the data center without them. And that's a much better way to have a pulse of your data center than to actually go do deep analytics on logs. So there's some value in logs, most of it in search, and we feel very little on analytics. Okay, so in terms of problem characteristics, this is very unique and different from most of the services I've dealt with before. For example, partial loss of availability, especially for older data, is an inconvenience. It's not a deal breaker. Cost controls are hugely important, and by cost controls I mean total cost controls. You do not want to keep putting too many resources on a problem like this, both human or machines and compute, etc., because it doesn't pay back too much. You really want your human investments in a service like this to be sporadic, right? And that's what you should expect, and that's what you should expect from the get-go. Scalability is straightforward. Scalability is usually a function of the problem. This problem partitions well. Writes need to be visible only lazily. Data is immutable. Read rates are very low. Write rates are high, but it's not at all easy to scale. It's pretty easy to scale. Sorry. Okay. All right. So I'm going to start with our Hack Week version, which is I think a fairly reasonable template for most people. A lot of people, when faced with a problem, do this, right? You build a pipeline from your clients to an Elasticsearch cluster. And in our case, we built a scribe pipeline that writes data to Kafka. And the Elasticsearch cluster picks up data from Kafka. The only services we actually own in this picture are the Elasticsearch cluster and fan-out search. Elasticsearch cluster. The fan-out search shouldn't be there. This is an older slide. It's got some errors. So Elasticsearch, for those of you who don't know, is a distributed search engine. It's open source. It's great for starting up on problems like this. It basically is a Lucene-based distributed search. It gives you scalability through sharding, and it gives you availability by building replicas. Okay? It's very simple to get started on. And the reason this was good enough for us was, well, we didn't know our requirements, and we didn't know 2 months later whether this would be a viable service or not, honestly. So we focused all our attention on doing integration so that you could go to Python, Scala, Java, whatever it was easy to send data to our service. And that's all we focused on. Initially, we were actually begging people to come try this out. But at some point, something changed, right? There were a couple of incidents where people lost their logs, and suddenly, within a couple of months, our rate grew very fast, and too fast for this particular ecosystem to actually manage. And it's not really a design issue. We haven't, this particular picture doesn't really have any architecture behind it, right? But anyway, at some point, we did get all our requirements. And so we had to consider 2 paths, either to take this forward by building all the additional pieces around this to make it work for us, or try a completely new approach. And we evaluated both and went with the new approach, okay? And to justify that, I'm going to go list all the requirements that we have, and then sort of go through the architecture of like how did we get to our current system. Okay? Okay, requirements. We want friction-free onboarding, okay, which means that, again, this is an older slide, so it's a little bit organized different. But yeah, so friction-free onboarding is a must, because first of all, we want to operate with partial resources for a service like this. So you don't want customers constantly asking you on how to get onboarded, because it's a cost on both sides, and it's a terrible first experience. We didn't do too badly in this model, in the Hack Week model, where it was easy to actually send, okay, where it was actually easy to send data to us. The real problem with the Hack Week model was that we it made it a little too easy. Rate control wasn't there, and the only place we could do rate control was through plugins in the Elasticsearch cluster. And that's a terrible place to do rate control because a lot of clients in the data center writing to a sequential stream using fairly expensive aggregators will overwhelm your ability to read from those sequential streams. So, so we were really struggling to do rate control when there were huge spikes of logs sent to us. In terms of performance, we were targeting 1 to 2 Gbps of peak ingestion rates. Our current ingestion rate is about 250 to 300 Mbps per data center. 6 months back, it was 70, and then I think 8 months back, it was 0, right? Something like that. It's not query heavy. Even 100 queries per second is too much of an ask. We get like 2 to 3 queries per minute right now. You need logs searchable within a minute of generation, and that's an expectation from all users. In terms of data loss, for a system like this, a little bit of data loss is impossible to avoid. The reason is, until the point you make data durable, it is, you are going to get data loss. And you can't move the first point of durability all the way up to the clients. It's too expensive for a problem like this. Okay? But there are other types of data loss we hit with the Elasticsearch architecture, which is, at least, I don't know if it's true in the recent versions, but in the old versions, if you lost a shard, you would have to throw out a lot of data, almost the entire index, right? So if you had a corruption in one of the shards, you'd lose the ability to query the rest of the index. So you want to avoid things like that. Okay? And so now we're coming to the more important requirements, because with just these requirements, it was easy to sort of patch up that ecosystem and move forward. So I'm going to talk about tiered availability next. So the value of logs just drops dramatically after the first hour. So the value of real-time logs is fairly high, because if there's an incident, you want to be able to troubleshoot it. You want those logs to be available. Up to about 4 hours or so, we do get a reasonable number of query volume. And after that, it just drops to 0. Nobody queries older logs. It's very, very infrequent. Okay? So you do want two tiers of availability. You want to prioritize availability of real-time data, and older data is sufficient if it's available within 5 minutes. Now, Elasticsearch provides high availability, but that's not this, right? And the reason is, for example, if our rate control mechanisms are horrible, and we're not able to keep up with the stream, you will keep indexing older data in an attempt to catch up, as opposed to going and indexing newer data. So that's not a pattern that works really well if you just keep this model. A second kind of issue is, if you have a slow node, Elasticsearch shards its data internally. So if you submit a batch of data to it, it shards it and starts writing to it. The single slow node can actually prevent catch-up on a bunch of streams. And so that's also not desirable. Okay? So you need to do some specific things to provide SLAs with availability SLAs like this. In terms of total cost of operation, dedicated hardware is horrible, right? You want to operate with a partial team. You do not want to do capacity planning. It's a complete deal breaker. You cannot you cannot run a service with dedicated hardware if you want to operate it with low costs, right? You truly want to minimize a resource allocation towards old data. It definitely doesn't make sense to lock up compute in the hope of serving the one query that comes on data that's like 2 or 3 days old. And the last thing you want is, if you go to a model where there's sporadic investments, you do not expect the same developer to come back and work on the project and take it forward, but you still want to enable it, which means you want to limit code, you want to have as little code as possible, and you want to delegate all your complex functionality to other data center pieces, and that's what we strive to do. All right, so in terms of these requirements, I'm going to get rid of friction-free onboarding first. How do we do it? It's very simple. Our clients integrate with our log library. They consume our log library. It's usually a single line change. If you take our Scala-based server, it's just a command line parameter. Most of the common log libraries are supported. Once you do that integration, you go to an admin page and request capacity. You say, what is the name of the index that you need? What is the rate at which you're going to be sending logs? And you give a contact, and you're done. And it'll provision the capacity for you at the back end. And then you deploy code and start searching. Okay? And our UI still looks kind of like the Kibana UI that we used in Hack Week, because people like the user experience, and we saw we didn't see any reason to change it. But the basic experience is you go put in your index name, you choose a time range, you put in a query, you get some histograms, you get a bunch of results. There's a small icon over there. You click on that, you get a personal dashboard for your index which says what's the rate at which you're sending logs, what is the rate that you have actually configured, and how much data are we dropping. Okay? All right, so I'm going to go build the rest of the requirements by starting with a stupid design, something that obviously doesn't work. And then in a couple of slides, we'll fix the issues with it. And so we get to what we have today. And the reason for me to do that is sort of I didn't want to throw a slide with a bunch of processes on it. It will be hard to explain that. So for the most basic design that you could do, this is something you could do in under 5 minutes, right? Clients send data to a set of partitioners. The partitioners partition the data and write it to sequential streams. You have a bunch of indexers. Each indexer is associated with a single sequential stream. It picks up data from there and indexes it. And you have a fan-out search process that goes and fans out search across all the indexers to produce results. So in this diagram, it's pretty much only the indexes which are stateful, the partitioners are stateless, and fan-out search is stateless. And clients we don't own, of course. Okay? So the first problem I want to solve is to say, well, we want retention periods. That's something we want to solve. And then we want these 3 tiers. The first one is we want high availability for real-time data. And the indexers have to serve real-time data. There's no question about it. You want a configurable amount of data served instantly or near instantly, at least best effort. And then you have older data that should only be served on demand. So we want to sort of do that tiering, right? So the model is, it's the same model for how data flows in and how indexers index it. Each indexer rolls indexes, creates a new index, closes an index every 10 gigabytes or so, and pushes it off to a distributed file system. Okay? And there's a retention manager that's responsible for where data is located in this whole system, right? So as soon as an index is published to the file system, to the distributed file system, it pushes it to one of the cache nodes. The indexer continues to serve whatever is the newest index that it's building. When that index gets old enough in cache, it's kicked out of cache, and it's only available on the file system. If a user wants to access really old data, they run a query against that data range, and they get back a result which says there's archive data. And they click on that link, and we tell them it's going to take 5 minutes for the data to come. You can continue searching, but the data will start becoming available. And when that request comes into the retention manager, it basically assigns all those indexes to free cache nodes. Okay? And once data gets old enough in the file system, the retention manager basically deletes it. So in this model, again, partitioners are stateless. Retention manager is stateless because all it's running is idempotent algorithms that match up what snapshots need to be in cache versus what cache nodes are alive. Cache nodes are also stateless because all they need to do is something when the retention manager tells them that they need to go load a snapshot from the file system and serve it. And so if they go down and come back up, they behave like an empty cache node, and the retention manager eventually assigns it an index. So what we have left is just the indexer, which is stateful. And so to fix that problem, what we did was indexers continue to operate the same way, but they're stateless now. When the indexer dies and starts back up, it queues a task for the data that was lost. So let's say it takes an hour to build a 10 gigabyte index, and you're 45 minutes into that hour. It dies and comes back up. It's going to queue a recovery task for whatever offsets it indexed in that 45 minutes and start from the head of the stream. So indexer still gives you real-time data. And the recovery instances are very few really large instances which can go index the same 45 minutes of data in 5 minutes or so. Okay? So that means all older data is still available under 5 minutes. Real-time data is still available through the indexer. So that's the final design that we have. Sort of to go over a few things, partitioning. So there's two fundamental ways to partition, two extreme ways to partition. One way is to take all the data that comes into the partitioners and spread it across all the sequential streams that you're writing to. The drawback of that approach is that if you want to restore some slice of data for a particular user with a low rate, you're going to have to restore a tremendous amount of data. And the second drawback of that is as the system scales out, the fan-out search is going to fan out more and more, and then tail latencies will become a serious problem. Another extreme is for every user that comes and registers with us, we give them their own sequential stream. So the partitioner goes and allocates the user to a sequential stream. And we have lots and lots of tiny indices, and that doesn't make a whole lot of sense either. So we took sort of a hybrid approach, which is each of those sequential streams is allocated a bandwidth of about 2 Mbps. The bandwidth is split into some whole-sized units. So some streams have 2 1 Mbps streams. Some streams have 10, 20, 100 Mbps streams, etc. Right? So when somebody says what rate they want, we allocate them streams based on 2 constraints. One is they need at least a minimum of 3 sequential streams allocated. So if one goes down, we're still able to serve we're still able to get their writes through the other 2. And the second constraint is you want to allocate them in as few streams as possible. So that's the provisioning logic. So when you go ask for capacity, that's what happens. The metadata is created to put customers on some of these partitions, and the partitioner honors that partitioning scheme. Second thing is rate control. Rate control happens at the partitioners. There's no durability yet. It's very easy to throw away data. The advantage of doing rate control at the partitioners is that all the systems downstream can be tuned once, and they don't have to be retuned at all, because every indexer is not going to see going to see between 2 and 4 Mbps of data. It doesn't have to be built to index anymore. Okay. In terms of sizing, all our indexers are, I think, 1 core approximately and 1 gig of RAM. The cache instances host 10 indexes each. Each of them is about 10 gigs. Actually, with compression, it's only about 5 gigs. So 20 instances perhaps. So it has about 100 gigs of RAM, 100 gigs of disk space, 2 gigs of RAM, and 2 cores, right? So we pack a lot of older data in one big instance, and we don't allocate a lot of capacity for it. As I said, the inbound rates are about between 200 and 350 Mbps in a day. There's daily variation. And generally, the number of documents we index per second are between 300,000 and 400,000 documents per second. In the cache tier, we keep only between 20 to 50 terabytes of data. Everything older than that is in the distributed file system. And so this whole thing took 2 developers about 4 months of work, and it's only about 10,000 lines of code. Another 10, 12,000 lines of tests, maybe. What is the other thing I want to in terms of perf tuning and scalability, the only real point where you have to revisit and tune is the partitioners, because everything else in that system is bound to fairly local. It's built to a certain spec. It doesn't have to change. So that's a big advantage. I wanted to put technologies to what we have, although I don't think it's super relevant. But the pipeline from the clients to the partitioners is Scribe. The sequential streams is Kafka. We use HDFS for to store all the indexes, and the rest of them, obviously, stateless services running on our compute tier. All right. In terms of future, we have a bunch of siloed products that do distributed debugging. We have, obviously, our metrics infrastructure. We have some things that deal with exceptions specifically, and we have sort of log management. And so the future is try to figure out if there is something we can do that can make all this, the sum of parts better than the whole. One other scenario we want to address going forward is this stuff works really well if you're going to do range searches. So you know what you're looking for. So because that limits how many shards you hit, right? And you don't have to bring a lot of indexes into cache. But suppose you didn't know when something happened. You're just looking for something across all the dates for which indexes are stored. Then this becomes sort of a painful way to do it, because you have to bring a lot of data in and out of cache. So if you could just do it using a batch-oriented thing where you could move the compute to where the indexes are as opposed to bringing it into cache and trying to search for it, that would be a better approach. There's not a lot of use cases for it yet. It happens every once in a while, but it's not frequent enough yet for us to go invest in it. There's other scenarios like auditing and stuff who want longer retention, like a year or so. It's fairly easy to add that into the system, but that's something that we need to do. One of the changes we could do is instead of using Kafka without replication, which is what we do right now. So that's a place where you can actually lose data. There's some other options within our data center which do replicated sequential streams. We could switch to that. And the last thing is we abuse Zookeeper like crazy because we use Zookeeper for all our metadata and change notification services, and the amount of data in Zookeeper is getting somewhat large. At least at 1 Gbps, it will get large enough that we'll have to consider separating change notification and how we store metadata. Yeah, and that's it. Questions? Yeah.
The backend DFS that you talked about, so you were trying to emphasize the recent data, and you would like to provide better service for the recent data, right?
Could you repeat that? I'm sorry.
So is the DFS is the repo storage place for all the data?
It's HDFS actually.
It's an HDFS. So
yeah.
how do you use snapshot or use compression inside? Like how do you do it for how do you manage the old data? Do you parse them eventually after a certain retention period?
Oh yeah, we throw it out after a certain retention period. So let me go back a bit. That didn't work. Yeah, so the retention manager has 3 tasks, right? One of them is to decide what data stays in cache. That's data from now to 1 day older. And then beyond 7 days, we throw it out of HDFS.
Hello. Could you please bring back the slide with the user interface?
Yeah.
Basically my question is, do you do the full text index on the logs?
That's right.
And do you use any knowledge of like the log structure and like do you parse out like the dates and
yeah, so we send JSON, and so there are a lot of fields that we custom index, right? Because it's Lucene allows you fields and it has a reasonable number of data types, right? So the log structure is controlled because our clients integrate our library. So when they do log.info and they put a text in there, we construct JSON out of it. We put in a bunch of additional stuff to help debugging. And so you can use that to search. But the search is the basic Lucene query parser for the most part.
I see. So how large is the, I'm sorry, that's the last part of the question. So how large is the Elasticsearch cluster that you use?
We don't use Elasticsearch. We went away from Elasticsearch. The last model, it's just boilerplate Lucene code. There's no coordination between indexers.
I see.
And that was very desirable, right? So if we have some developer coming in after a month just to work on these pieces, the amount of coordination Elasticsearch does and the amount of work we need to do to run it in a stateless service would be quite high, right? And so we chose to instead write 10,000 lines of code and build a service out of these small, tinier pieces.
So what is the ratio between the size of your cluster and the working cluster?
In the original Elasticsearch cluster?
No. You have your cluster that runs the indexers and everything else, right?
Yeah, but this is a shared
log.
compute platform. Think of it as EC2 or something like that. It's for all of Twitter. It's all our shared services run on this compute tier. And we run 100 indexers, each of them taking a core and about 1 gigabyte of RAM.
So what is the ratio between between indexers and the clients? Like, I don't know, 1,000 clients per indexer or something like that.
So there are a few hundred services. I don't know exactly how many clients. At the end of the day, it's going to be pretty much most processes in the Twitter data center. And I don't know, I don't really have a good count right now in my head, so I don't want to misinform you.
Could you give us a sense of the scale, like how many machines are being used, how much
So
data?
I can quickly calculate. So in terms of indexers, which do about 300 Mbps, right? You need approximately 150 indexers, which do 1 core and 1 GB of RAM. We don't use machines. We just go on the computer, right? Cache is 50 terabytes. Each cache node handles about 200 gigabytes, 100 to 200 gigabytes, and it uses 2 cores and 2 gigs of RAM. And so you just multiply it. As you scale, you can just multiply.